Hi everyone, welcome to today's webinar. This webinar is being brought to you by the Offshore Wind Accelerator Project, also known as OWAP. OWAP is managed by the Clean Energy Group, and today's topic is Maine offshore wind milestones. Today I'd just like to start by going over some quick housekeeping. All of the participants are in listen-only mode, so you can hear us, but we can't hear you. You can either listen to the audio through a telephone, and then you will need to type in the PIN number that you see on your keypad, or you can listen in through your mic and speakers on your computer. We will be reading questions. If you would like to submit them throughout the broadcast, you can type them in on your console in the question box and hit send. We will have time for questions and answers at the end of the webinar. And this webinar is going to be recorded and it will be made available on our website. And you can see the URL on your screen. And now I would like to introduce Val Story. Val is the project director for OWAP, and she is going to introduce today's guest speakers and talk a little bit about our webinar today.
Hi everyone, thank you for joining and welcome to today's webinar. As Samantha mentioned, this webinar is being brought to you by the Offshore Wind Accelerator Project, which is managed by the Clean Energy Group and the Clean Energy States Alliance. They are sister national nonprofit organizations working on innovative renewable energy technology, finance, and policy. And the Clean Energy States Alliance specifically works with state clean energy funds working to promote clean energy markets and technologies. To that end, the two organizations run the Offshore Wind Accelerator Project. We have 5 main focus areas. We work individually with states. We work one-on-one to develop policy strategies and strategies for reducing costs for offshore wind development. We have recently been focused on coordinating information sharing on policies from the UK and sharing information about EU offshore wind lessons learned. We continue our work in communicating ideas and policy developments through our communications network, such as our newsletter, our Facebook, and our Twitter services. So if you haven't signed up for those, there will be a link at the end of the presentation to get you more information. And lastly, we work regionally trying to encourage regional cooperation to increase opportunities for joint funding, joint information sharing, and supply chain development. And we are working on new finance tools and mechanisms. We have 2 presenters today. I would like to introduce you to Dr. Habib Dagher. He will be presenting first. Dr. Dagher is the founding director of the Advanced Structures and Composites Center, a National Science Foundation-funded research center housed in an 83,000 square foot laboratory with 140 full and part-time employees. The Composite Center is a world leader in the development of low-cost and high-performance structural composites for construction. Dr. Dagher himself has conducted over 125 research and development projects with a total value of over $65 million. He's received funding from agencies such as the National Science Foundation, the U.S. Department of Energy, the Office of Naval Research, the U.S. Department of Commerce, the Federal Highway Administration, and the U.S. Department of Agriculture, the U.S. Army, and the U.S. Coast Guard. Our second presenter is Attorney Jeff Thaler. Attorney Thaler has been legal and permitting counsel for the Maine offshore wind project since their inception. He is a visiting professor of energy policy, law, and ethics at the University of Maine and the Maine School of Law, as well as assistant university counsel for environmental, energy, and sustainability projects. He has been developing and teaching courses on renewable energy law, energy economics and law, administrative law, and climate change law and policy. He graduated magna cum laude from Williams College and from Yale Law School. Before joining the University of Maine, Jeff developed over several decades a wide-ranging legal practice focusing upon environmental and energy permitting, compliance, enforcement, and litigation. Today we will be hearing about the nation's first grid-connected offshore floating wind turbine prototype off the coast in Maine. The project is led by the University of Maine's Advanced Structure and Composites Center, and the prototype represents the first concrete composite floating platform turbine to be deployed in the world, and this attests to America's innovation and leadership in renewable energy technologies. The turbine, which we'll hear about, the VolturnUS, is a 65-foot prototype at 1/8 scale of a 6-megawatt turbine. And the future plans are for this prototype design to be scaled to build 2 6-megawatt floating turbines and a 12-megawatt pilot floating offshore wind farm. The proposed farm is the Aqua Ventus 1, and it's under consideration by the U.S. Department of Energy to receive a $46.6 million award. Back in 2012, it received an initial award of $4 million. So over the next half an hour, we'll hear from Dr. Dagher and Attorney Thaler about recent milestones achieved, including recent approval by the Maine PUC for the power production term sheet, and we'll hear about the next steps for this project. As Sam mentioned, any questions, please type them in the questions box, and we'll address them at the end of the webinar. Thank you. Dr. Dagher, you are up.
And you'll just need to, there you go.
Bear with us a moment as we load our slides. And Dr. Dagher, don't forget to unmute yourself once you're ready to present.
And Dr. Dagher, we can see your screen, so if you could put it into presentation mode or unmute yourself if you're having some difficulty, we can guide you through it. You're on mute by, you can unmute by hitting the green icon next to your name on the staff list. Okay, folks, sorry for the, here we go. We can hear you now. Can you
hear me now? All right.
We can hear you now. So you need to put this into presentation mode.
Thank you.
Okay, here you go. Thank you.
Hello, it's a great pleasure to be here with you today. I'm going to talk about the VolturnUS floating wind turbine technology, and then Attorney Jeff Thaler will talk about some of the permitting efforts in permitting our offshore wind farm. I'd like to acknowledge the Department of Energy for their support on this program for a number of years, particularly Jose Zayas and Greg Matzat and Michael Hahn and many others at the DOE. The National Science Foundation, who supported quite a bit of this effort as well, the Maine Technology Institute, and many others. I'd also like to acknowledge over 30 partners who've worked with us on this program. You can see some of them on the screen right here, including the Chimbro Corporation and HCR and TY Lin International, Emera, Iberdrola, and many others. In terms of what I'll talk about today is I'll tell you who we are. I'm going to focus quite a bit of this work on giving you an update on the results of the testing of the 1/8 scale VolturnUS floating turbine that we deployed in the beginning of June here off the Gulf of Maine. We've had some very exciting times in terms of the offshore wind environment and wave environment off the coast of Castine, Maine. And I'll finish up with the DOE Advanced Technology Demonstration Project and where we're heading with that program. A bit about us. I work at the Advanced Structures and Composites Center at the University of Maine. We have about 200 people who work in the lab now. We're 87,000 square feet. We've been in operation for 18 years. And we've funded financially 1,400 students who worked through the lab over the years. And we work with with the composite industry and the construction industry to bring advanced materials into construction. And as you will see from the work we've done, the approach to bring the cost of offshore wind down for us is to introduce new materials and advanced materials to drive those costs down in new construction methods. And that's where our expertise and strength is. Our program has received the Global Industry Awards in Advanced Materials by the American Composite Manufacturers Association and many other groups. The American Society of Civil Engineers has given us the most creative most creative product developed in 2011 in the United States. This is the technology called the Bridge in a Backpack that we've developed. This is a U.S. composite boat for the U.S. Navy SEALs that we've developed as well. A bit of why we're doing what we're doing here in Maine is most of us use heating oil to heat our homes, and this is a cost of heating a typical Maine home from Efficiency Maine, and you'll see here in red on the right-hand side, it costs about $4,000 a year for the average family to heat a home using oil. But if that home went to air source heat pumps using electricity, that number would go down to about $1,624 a year. So a significant potential reduction in the cost of heating for a Maine family if we switch to electricity. So the question is, where does this electricity come from, and can we use offshore wind to bring some of this electricity into the state? This is a chart that shows the average Maine family budget in 10-year increments. Each pie represents the family budget in 1998, then in 2008, in 2012, and eventually in 2018, what our projections look like. What you see in blue in each pie are the energy costs for the Maine family. That's 5% in 1998 of the family income was used for energy. The yellow part is the healthcare costs for the family, and the green part is what's left to live on once the family paid their energy bills and their healthcare bills. So as you see here in 2008 and 2012, when heating oil as well as gasoline reached $4 a gallon, about 20% of the family income went to energy prices. So it's a major issue for the family. And then as we move towards 2018 and beyond, as the prices of heating oil and gasoline will go up, it's going to become harder for families to make ends meet. And that's one reason we're looking at moving into renewable energy sources to, in the long run, reduce the cost of energy for the family. The Northeast United States has about 55 million people. You see that area in blue on the graph, and the best offshore wind resource on the east coast of the U.S. Off the coast of Maine alone, there's about 156 gigawatts of offshore wind within 50 miles of the coast. So one of the plans that we have is work throughout the Northeast region, the New England and Northeast region, to deliver offshore wind into this region. One feature of our environment is that we have deeper waters off the coast of Maine and Massachusetts. As you go farther out, about 300 feet of water depth, 100 meters at about 2 miles from shore, so 2 to 3 miles from shore. So we are looking at floating technologies to deploy offshore wind. The state of Maine put together a plan to produce 5 gigawatts of offshore wind in the 2030s, by the 2030s. That's an ambitious plan that was put together a number of years ago. And the goal was to use over-the-horizon farms that would be placed floating farms that we placed beyond the horizon. And the purpose of that energy is to help put that on the ISO New England grid. So it's a New England-wide effort. And also to help heat homes, as I told you earlier, as well as help deploy plug-in electric vehicles in our state and in the region. The 5 gigawatts is enough energy to heat every home in our state and to fill every plug-in electric vehicles in the future in our state in the next 10 to 20 to 30 years. Our effort is broken up into 5 phases. It's a walk before you run, and run or crawl before you walk approach. We started out by building 150 scale models of different floating wind turbines to determine what works best for us. And then in 2013, in our phase 2 program, we deployed a 1-to-8 scale prototype off the Gulf of Maine to learn from that effort. And then now we're in the process of developing a 12 megawatt scale project. It's under the DOE Advanced Technology Demonstration Program that will be plugged into the grid in 2017. And that's our phase 3. We'll monitor that for 5 years. And following that, we would be ready to build larger scale farms in the 500 megawatt range. Our phase 4 program, the commercial development of floating offshore wind, we believe will happen in the 2020s. And will continue into the 2030s to reach about 5 gigawatts. Our major challenge that you all know is how to bring the cost of offshore wind down. This chart shows you the cost of electrical generation in the state of Maine. That's historic costs for small, medium, and large customers of the Bangor Hydroelectric Company, or Emera in this case. We started out about close to 4 cents a kilowatt hour in 2000, and we've been fluctuating a bit down in the year 2010 as natural gas prices went down. But we're still at in the order of about 8 cents a kilowatt hour on the generation side. That's going to go up because of the reduced availability of natural gas to our region. It's been going up recently. But as you try to project that into the future, our goal is to try to, with bringing offshore wind down, is to reduce the cost of offshore wind, particularly floating offshore wind. So these two curves, the actual cost of electricity today and the cost coming up from the future, coming down from offshore wind, will meet somewhere in the 2020s. How fast we'll be able to drive the cost of floating offshore wind down will depend on when we start. This is a learning curve type approach to where the technology will go. So when we start, we'll determine how fast we can bring some of this down. We think it would be feasible to get to the cost of generation of electricity in our region. I'd like to remind you we have some of the highest electricity costs in North America in our region. So our ability to bring offshore wind down to meet those costs is our goal. Our technology that we've looked at helps avoid some of the expensive offshore wind construction assets that don't exist in our New England region. Our New England region does not have the jack-up barges necessary to deploy offshore wind farms that Europe is deploying right now. We don't have the large cranes and heavy cranes that we would need to place on these offshore barges. So we've been looking at ways to avoid that by going to the floating technology. We looked at 3 different types of floating wind turbine designs as part of our comprehensive effort of crawl before you walk and walk before you run. We designed 3 floating hulls for 5 megawatt turbines a number of years ago. These are 150 scale hulls that were placed in a wave wind basin, and each one of those hulls was subjected to 60 different Metocean conditions from the Gulf of Maine. And those hulls were instrumented with sensors to look at the overall global motions of the hulls, and they had turbines that are fully operational on these hulls as well. It's the same turbine on all 3 hulls. We learned a lot from this experiment. What we've learned really is that all 3 designs are viable, and the choice of the design and the choice of the materials depend on where actually you would like to build these. And that's the key to this, is we can make them all work, but the question is what works best for your particular region. Our paradigm shift, we believe our VolturnUS paradigm shift, is when we chose here to get away from using steel for these units and go to a concrete hull for the units. The reason we did that is the cost of steel in our region is very high. Fabricated steel is very high. We don't have large-scale steel fabrication facilities in our region that will compete with Southeast Asia prices for steel, fabricated steel. And in the U.S., we've actually lost our steel hull boat building capabilities to Southeast Asia because of the costs of production in the U.S. So we went to concrete for that reason, and one of these reasons, and because we believe we could produce concrete hulls in our region at prices that compete with steel imported from overseas, as well as steel, of course, produced here in this region. So we're using concrete construction methods, as you see here, precast construction methods, and have partnered with civil engineering companies that can produce these. So the paradigm shift is, rather than using oil and gas assets, steel fabrication assets, jack-up barges to produce these offshore wind farms, we're using civil engineering construction methods and civil engineering contractors that build precast concrete bridges. It's a modularized approach for construction to drive the cost down. And it provides also corrosion resistance opportunities. By also going to floating wind turbines, we can go farther offshore in the Gulf of Maine, and we've seen capacity factors, gross capacity factors in the Gulf of Maine that exceed 50% in the region where we'd like to go, and average wind speeds in the 9 meters per second range at hub height. So that those floating technologies allow us to access a much better wind resource farther offshore. This is the 1:8 scale prototype that we built in our laboratory at the University of Maine. It's a 1:8 geometric scale prototype of a 6 megawatt turbine. And this is the prototype assembled dockside before it was placed in the water on May 31st of 2013. What you see right here is the concrete hull. We also use a composite tower on this unit to drive the cost down and the weight down. A composite tower on a 6 megawatt unit allows us to cut the weight of the steel tower by a factor of 2, and then take out 2 to 3 times the weight of that weight reduction from the hull as well. So for every pound of steel or kilograms of steel we take out from above the water, we can take out 2 to 3 kilograms or pounds of steel from below the water. What you see here in red are the area that's for the water line. The red line and yellow lines are where the water line is in this. So everything in red would be submerged. Everything in yellow would be above the water. So we placed that whole unit, that whole system in the water as one unit, and towed it down the Penobscot River for about 30 miles to its final location off Castine, Maine. The tow-out was one of our first experiments in this project, is to prove that this technology, this particular design, can be towed out efficiently. We had a number of sensors that measured the forces in the tug line as well as the motions of the unit during the tow-out operation. And that was a successful operation. This is the tow-out. We had only one tugboat up front, and we had a trailing tug to help steer the unit if necessary. One of the most important parts are the scaling studies that we've conducted on this project. The question is how do you get the most out of a scaled experiment? And that's not a very simple challenge. The challenge is, can you really truly have a good scaled experiment? And then when you're further offshore, can you truly characterize the environment accurately enough to verify the numerical models and verify the performance? So these are major challenges we've taken on. Our approach to scaling was to find a site that has 1:8 scale waves, and we did some modeling of the Gulf of Maine, wave modeling that identified a site, a protected site off Castine, Maine. It's about 1,000 feet from shore that has a 1:8 scale wave environment. And in order for us to scale the wind, we couldn't do it directly. So what we did is actually scale down the rotor size so that we produce a thrust that represents the correct scaled thrust on the turbine. So this dotted line shows you the actual rotor diameter relative to the full-size scale. But the rotor diameter, as you see here in the scaled experiment, is smaller, and that's in order for us to match the thrust, the correct thrust at the scale. I'll show you, first start by showing you the tow-out operation down the Penobscot River. So this is a trailing tug that you see on the right-hand side, and this is a unit going down the Penobscot River. You can see the relative size of the waves in this case. You can see the movement of the trailing tug here and versus the unit that's quite a bit more stable. Again, we towed it down about 30 miles. It took close to 12 hours to tow it down the river. When we arrived to the site, this is the leading tugboat that towed the unit, and that's the trailing tug that allowed us to steer the unit if we needed to. And then when we arrived to the site, we had pre-installed drag anchors and mooring lines that were attached to the unit, and we installed an undersea cable that attached it to the unit that was also laid on the seabed. The unit had over 50 sensors on the unit, and I'm going to show you some videos on the performance of the unit during operations. Because it is a 1:8 scale, we're able to see significant events very quickly in terms of relative size of the waves to the size of the unit. We're able to see events in a 100 to 500 year return periods in November and December and January. So we've collected a lot of valuable data. One of these events occurred on November 1st at 1:59 p.m. This is I'm going to show you a video of that particular event. Another event I'll show you occurred on December 15th during a snowstorm. I'll show you in just a minute those videos. But in order for us to collect good quality data to validate our models, not only did we have sensors on the unit itself, we had over 50 sensors, but we also built a LiDAR and validated the LiDAR next to the turbine. This is the LiDAR that you see on the right-hand side. It was also built in our laboratory, and it has the ability to recharge using both solar as well as wind turbines, vertical and horizontal axis wind turbines. It's designed to operate autonomously for 6 months and be able to recharge autonomously for 6 months. And you can see here a correlation between two LiDARs, one placed on land, one placed offshore. So it's the data collected by the LiDAR, which is the wind data as well as the wave data. It had wave and wind collection capabilities, as well as the data collected at the unit itself that allowed us to compare to the models that we developed. I'm going to show you the videos quickly here, and then following that, show you some of the results we're looking at. This is the video that occurred. One of the videos for an extreme event that occurred on November 1st. This is a camera that's on land, that's looking out at the unit. It's about 1,000 feet from shore in about 80 feet of water. And that's starting at 1:59 p.m. on November 1st. This is when we saw an event that's between 100 and 500 years in terms of wave height. At that time, the unit was running, and the thrust that we have on the unit was equivalent to the full design thrust on the turbine. So we saw essentially 100 to 500 year return period waves as well as a full thrust on the turbine at that time while the turbine was operational. And the video will show you in just a minute some of the numbers in terms of wave height as well as wind speed. The wave height was about 8.8 feet here. You see that you would multiply that by 8. That would get you almost 70 feet at full scale. And that corresponds to a return period more than 100 years on the event. And this compares the event we saw on November 1st to Hurricane Sandy, which you may all remember, that had a 32.5-foot wave height, whereas the event we saw on November 1st had an equivalent 70-foot wave height. A 100-year wave height was 64.1 feet. So a 500-year wave height was 73.2 feet. So we're pleased that we were able to measure the performance of the unit during such extreme events. And during that event, the maximum acceleration that we measured at the tower base was about 0.165 g, and the maximum angular acceleration was about 0.166 radian per second square. The wind speed was about 41 miles per hour at the time, and the maximum inclination angle was 5.9 degrees. That's very close to what we actually had modeled. So it was very very fulfilling to see that our models and the performance in extreme events were very close. The other video I'll show you was a windstorm that also created over 50-year return period events for us. This is called windstorm Electra, or snowstorm Electra, I should say, and that occurred on December 15th. It was dramatic video because you could see the fog going across and the snow going across the unit. But again, if you look at the relative waves at that particular time, the waves were equivalent to 50-year waves events during the Electra storm. And as you see here, you can see very little movement of that unit during that event. If you recall, during a 100-plus year event, we saw a 5.9 degree inclination angle. So we're getting quite a bit less than that during this particular event. And as you can see, you could barely see the motion of the unit during the event. Again, these events allowed us to collect very valuable data to compare to our models, and I'll show you some of that data here. Again, the November 1st event, very quickly, that event is an equivalent to a 21.5 meter wave. And if you see that, that's between a 100 and a 500-year return period wave for the Gulf of Maine. And during that event, the maximum inclination angle we saw on the unit was 5.9 degrees, and then maximum acceleration at the base was 0.165 Gs. Looking at the data in more greater detail for November 1st, you can see here in the first row the actual measured acceleration, linear acceleration, angular acceleration, heel angles during that event, as well as the thrust, the mean thrust on the unit. That's the scaled values of that, so you multiply by 8, particularly some of these values, the wave heights get multiplied by 8 when you scale it, whereas of course the accelerations does not scale. And the angular acceleration does scale in this case. Heel angle does not scale, it's exactly the same. And the mean thrust, of course, scales. And that gives us the numbers for a full-scale deployment, 6 megawatt full-scale offshore. And this is the simulation results from what we call DLC 1.6. That's the design load case, 1.6, and that's just all simulation results. And that design load case 1.6 has a wave height of 21.1 meters. That's what we simulated, versus the actual measured during that time was 21.5 meters. So what we simulated for DLC 1.6 is not exactly what we measured, but you can see here at the very bottom in dark how close that event was to a DLC 1.6 event. That's an extreme design case event in this case. So in this case, the wave height was 102% of the DLC 1.6 event. The linear acceleration was 93% of the DLC 1.6. And the angular acceleration was right on, was about 100% of the DLC 1.6. That's when we're comparing the scaled experiment to the DLC simulations. So again, simulation experiments are very close in this case. We're very pleased with our ability to simulate these events. The other challenge was, can you do a time series simulation? Can you simulate a time series response of the unit during the storm? So this is a time series record of during a 1 hour period of the wind speed here on the right hand side and the wave measured at the unit at that particular time. So again, 1 hour of wave, 1 hour of winds, and what you see here is the measured and scaled, the measured in blue, the measured PSD for that wave environment, and in red a scaled 500-year PSD. So you can see that what we measured on that particular day, on November 27th, is close to a 500-year event based on this simulation. And this is what we were able to do that shows a comparison, a time series comparison of the base sway and base heave acceleration during that event. And you can see on the horizontal axis the time in seconds, the sway acceleration on the vertical axis, and in blue and in red are the data that we measured. In blue and red are the fast simulations. And as you see here, we're able to pick out the peak accelerations in the sway direction very, very closely. On the right-hand side are the heave accelerations, which would be up and down. Sway is horizontally in the direction of the waves and winds. In the vertical direction and the heave direction, again, the blue curve are the time series of the data that were measured in the heave direction at the unit. And in red are the simulations that we've developed, the time series simulations that we've developed. Again, very close. So we're very pleased with our ability to predict what happens during these extreme events. And finally here, the last slide of data shows you a comparison of the angular acceleration of the hull, at the base of the hull, comparing again the data in blue that we measured for angular acceleration using accelerometers mounted on the unit, and in red are our numerical simulations using our coupled models. Again, very close simulations, and we're very pleased with those abilities to simulate the unit. So where do we go beyond that? Since we feel that we have a successful 1-to-8 pilot scale deployment, and that the technology has been proven out at least at the 1-to-8 scale, we're ready to go to the full scale, and that's part of the Advanced Technology Demonstration Program for offshore wind that's been put out by the Department of Energy. The DOE will be selecting the winners of this competition. We will be hearing about that in May. If we are selected, we will be connecting our turbines to the grid in the summer of 2017. That's when the 2 turbines will be connected to the grid. Our goal is to put in 2 full-size turbines using this VolturnUS design, where the hull is concrete and the tower is composite materials. We have a power purchase agreement that's been on the project. We have a lease already in hand for the site. The contractor that's going to build the project has been selected. The interconnection agreement has been tested, and there shouldn't be any issue to interconnect. We've done all the analysis for interconnection. And the permits should be available to us by 2015, and you'll hear that from Jeff Thaler in just a minute. We follow, because we are in state waters, we have a different permitting schedule than you would be if you were in federal waters. It's a state permitting methodology that we need to follow. Our 20-year power purchase agreement was awarded to a private firm. We have formed an SPV, that's a special purpose vehicle company called Maine Aquaventus. That private company will be building and operating this farm. The private company has received a term sheet approval from the Maine PUC in January for a 23 cents a kilowatt hour project. The Maine Aquaventus is made out of 3 main partners and 20 other partners that will come into it. The 3 main partners that manage the private firm are Chimbro. Chimbro is a company in Maine and is in 40 states in the U.S. that has 4,000 employees. Emera is a leading developer and operator of electrical assets distribution, and then Maine Prime Technologies is a spin-off from the University of Maine. Collectively, they manage the new company Maine Aquaventus. So it's a private firm that will build and operate this farm. The farm is located will be located off Monhegan Island, off the coast of Maine. Monhegan Island is about 12 miles from shore, depending on where you land on shore. And this is a state of Maine map right here, showing in red where the Monhegan Island is off the coast. The blue line here is a state water. It's 3 mile state limit to state waters. So the test site shown in orange is all in state waters. So the permitting part of this project is a state permitting effort. And as part of the permitting effort, we've done a lot of visual and sound modeling. It's part of the site. You can see here that's Monhegan Island looking out and seeing the 2 floating turbines here in the horizon. We've also done environmental baselining of the test site for over 4 years right now in terms of radar measurements of birds and bats. We've tagged fish at the site for the last 4 years and tracked their movements. We've had bird ID studies as well, and all that information, in addition to hundreds of community and stakeholder outreach meetings, were carried out between 2010 and 2014 and continue to be carried out. And with this, I will hand this to our attorney of the project, that's Jeff Thaler.
Thank you, Habib. And I guess I'm not sure if you have the next slide up from environmental baselining. Okay, so I mean, basically the environmental testing has been going on as Habib indicated. We'll be getting a general permit from the State Department of Environmental Protection that is pursuant to legislation. Because we're in a state test site and the cable will be running in state waters to shore, it's a 60-day review process from the time of a completed application. We've been consulting with all state and federal agencies. We had done an environmental assessment for the turbine that's currently in the water and had also evaluated the Monhegan site originally as well, and we'll be doing so, updating that for the full-scale project, and working on that with Department of Energy and the Army Corps, who are the lead agencies on it. We will also be getting a Section 10 Army Corps permit, which is required when you anchor to the bottom. So those will be the primary permits for the water deployment. We'll be bringing the cable to shore and connecting to the grid, as Dr. Dagher said, and so we'll have some local permitting. Our assembly site for the tower and turbine on shore will also require some permitting, but it should be fairly straightforward because of relatively minimal impacts, and that we'll be reusing sites that have already been developed. So overall, on the permitting of the project, we will be sort of following in footsteps that we've already carved out, and one of the unique aspects, again, of the project is being able to be so far offshore to capture the strength of the winds, as Dr. Dagher said, but still remaining in state waters. And that's in part because of the fact that the Gulf of Maine has, and the coast of Maine has so many islands, and under the federal law, if you're within 3 miles of the state island, you're in state waters. So with that, I don't have anything further on permitting. Habib, I don't know if you had anything you wanted to say in conclusion.
Yes, in conclusion, we believe we are on our way to obtain all of our permits for the site. Again, we have already a lease for the site from the state, so the lease is in hand. The permits will all be available in 2015, and the construction for the project will start at the end of 2015 and beginning of 2016, again to be plugged into the grid, as we said, in the summer of 2017. We're pleased that in Castine, Maine, in June of 2013, on June 13th at noon, the first offshore wind electron started to flow into the U.S. electricity grid, and they're still flowing today through this pilot project. That pilot project gave us significant information that leads us to de-risk, if you wish, the DOE Advanced Technology Demonstration Program, which will be operational by 2017, and then that will be operational and be tested for 5 years. Following the 5-year testing period of the DOE Advanced Technology Demonstration Program, we would be in a position to start building commercial farms of floating offshore wind off the Gulf of Maine. So thank you. This concludes the presentation for this effort here. So, happy to take some questions.
Great. Thank you so much, both of you, for a very informative presentation. We have several questions, so we'll get started there. And just a reminder to those of you who are still on, please feel free to type in your questions into the question dialog box. Okay, to start off, question about the water depth. If the water depth where the prototype model is currently moored, does that correspond in scale to full-scale deployment?
Yes, the water depth we have at the test site in Castine is about 60 to 80 feet, in that range. The deployments that we'll have farther offshore in the Gulf of Maine, if you would to multiply that by 8, that's very close to what we're looking at. It's a bit deeper than what we would be looking at, but fairly in the same range. The test site that we're going in has about a 100-meter water depth at the test site, and then farther off in the Gulf of Maine, when we go to larger farms, we'll be looking at water depth in the 100 to 250-meter water depth. So yes, the 1:8 scale does fit in within that range.
Did you say 250 meters, up to 250 meters?
Yes, 100 to 250 meters, depending on how far you are from shore. So.
Thank you. And a question about what the composite materials are.
Yes, the composite materials, again, there's a lot of proprietary information, so I can't tell you everything about the composite materials, but the tower that we use, the composite tower that we used, has been tested actually in our laboratory at near half scale under fatigue loading. We've simulated fatigue loading, the equivalent of 6 years of fatigue loading on that tower, and tested it to failure afterwards, showing the full residual strength after 60 years of fatigue. The materials we use, as well as the manufacturing methods we use for the tower, are all available methods. So we try to keep it simple, so we're not out there developing new methods that would be less reliable. So we relied on existing resins, existing fiber systems, and existing manufacturing methods for the tower. So.
Great, thank you. If the project is not selected by the Department of Energy for the next award, what are future plans for the project? Would it continue without DOE funding?
I would prefer to answer that question after we hear from the DOE in May. So, thank you.
Okay. Do you have any plans to deploy this technology outside of Maine?
Yes, there's been a significant interest. with this technology, not only throughout the United States but also throughout the world in a lot of the major continents. So we've had a number of requests to do some of these demonstration projects in other locations as well. So we have been focusing our efforts now on the DOE project, at least over the last couple of months, but have been talking to a variety of interested groups across a number of continents and other states in the U.S. as well. So.
Great. Thank you. Another question. Where will the cable be connected on shore? It's all will be in state waters?
Yes, the entire cable route from the Monhegan test site to the landing of the cable on shore is all in state waters, which is very helpful for us. And then there's an available interconnection very close to shore where we're going here, the available substation that we'll be connecting to. It'll be connecting to the central main power grid at an existing substation. The studies have been done for that substation, and it's able to take the energy, our energy right now. And so,
could you talk a little bit about the cost savings between the composite fabrication and the steel fabrication? What percentage of costs do you think?
Yes, it's a function of certainly the size of the turbine that you end up using and the type of hull you end up using. The unit is made with both concrete and composite, so I would assume the question relates only to the composite part of it, or also the concrete?
The composites.
Okay. In terms of the composite part, as I said earlier, roughly the weight of the tower, steel versus composites, when we go from steel to a composite tower, is cut roughly by a factor of 2. So we're using the weight of the tower is cut in half. And on a 6 megawatt turbine, the steel tower might weigh anywhere from 450 to 600 tons, depending on how you design your steel tower. The composite tower would be about half of that. So if you have a 250 or 300 ton tower, so you're saving about 250 to 300 tons of steel above the water. And below the water, you would be saving an additional 2 to 3 times that amount, depending on the size of the unit and the kind of hull you would use. So if you're using a steel hull, you would be under the water. You would be saving about 2.5 to 3 times that. So you would be saving roughly 300 times 2, 300 times 2.5, actually 200 times 2.5 to 300 times 3. So you might be saving from the under the water another 600 plus tons. So that's certainly very significant. If you have a concrete hull, you have, again, similar weight savings as well, depending on the size of the hull and the size of the unit. So, and then the cost savings become an issue of how much does your concrete tower cost versus the composite tower cost versus your steel tower cost, and how much reduction in weight for the hull and what the benefit of that is. Our numbers show that you do save money by going to a composite tower versus a steel tower for our concrete hull. And those savings also do translate to a steel hull if you do have a steel hull as well.
Thank you. Let's see. Someone has written, you mentioned that steel hull shipbuilding has significantly decreased, yet BIW is located mid-coast. Has BIW been approached about full-scale construction?
Yes, absolutely. When I said was decrease, is BIW makes essentially defense-related destroyers for the Navy. When I said decrease, I was talking about the commercial ship construction, steel ship construction in the U.S. Commercial heavy ship construction in the U.S. Has decreased significantly, as we all know, and a lot of that now is in Southeast Asia because of the cost of producing these in Southeast Asia versus the U.S. So that's what has decreased significantly in this country.
Thank you. Another question. One of the issues with offshore wind generation has been possible impacts of electromagnetic fields on marine fauna. Are there plans for studies of that sort and its potential impact?
Yes, our environmental ecological team has been looking at that in great detail, not only electromagnetic impact, but all other impacts on fish and other wildlife. A lot of that information, of course, we were lucky that we have a large body of data from Europe today, since they've been added since 1991 and have about 6,500 megawatt of offshore wind installed. So we're relying a lot on some of that data. In addition to that, we're of course collecting our own data on the impact of these on the environment. And our environmental ecological team has a very extensive environmental ecological testing effort that, as I said, started back in 2010 in terms of baselining the site, baselining the species at the site. And when we start placing the cable in the water, we're going to be evaluating, of course, the impact on the cable, not only the cable, but also the floating turbine and the noise levels and others on what lives under the water and above the water. So this experiment is not only a mechanical experiment, if you wish, but also an environmental, a very extensive environmental experiment, an ecological experiment.
What is the expected generation capacity of the full-scale 6 megawatt turbine?
Again, you can run the numbers fairly easily on that in terms of megawatt hours, but you're looking at over 30,000 megawatt hours a year, and the test site that we have has gross capacity factors close to about 51.5% for a 6 megawatt machine. And then you look at your losses and typical losses on that site, and then you back into the megawatt hours you would produce, but certainly in excess of 30,000 megawatt hours per year.
Great. And do you feel that this floating technology has cost-saving potential versus fixed foundations anywhere along the U.S. coast, or is it just particularly for deep water sites?
It's a very good question. The numbers that we've put together so far on this shows that we can potentially place these units in water depth of about 120 feet or more. So they fit in, if you wish, in what we call the transitional water areas down to the deep waters areas as categorized for deep water, for offshore wind. Yes, there's certainly the about 2/3 of the offshore wind, which is close to 74% of the offshore wind resource in the United States, is in deeper waters. So this technology has applications throughout the U.S., not only in Maine, and can allow us to capture energy in some of these deeper waters. The key to the deployment, to the cost reductions, in our opinion, will be the use of concrete. In our case, the ability to produce these units using existing civil engineering contractors that use concrete technology and methodologies for construction that already exist, so we don't have to go out there and build very sophisticated manufacturing facilities for steel, and avoiding the need for jack-up barges and cranes, and being able to locate these in areas where you have much better wind resource. If you are limiting yourself to shallower water, you're limiting yourself to the environment and the wind resource that you could actually place these units in. So based on our modeling, we believe that floating offshore wind, yes, would be able to compete financially with fixed-based offshore wind. The key for that, as I said, is the concrete designs that we've developed, the composite tower technology, and as well as scaling up the technology. And for us to get there, we need to scale it up. So.
Great, thank you. That is it for questions that we have. Dr. Dagher or Attorney Thaler, anything else to add this afternoon?
No, we'd like to thank everybody for joining us today, and we're certainly, if people want to have further questions, we're happy to answer them if they want to email them to us. So.
Agreed.
Great. I'd like to thank both of you again for your time and for all the information you've presented on today's webinar. Up on the screen are some links and an email address for how you can stay connected with the Offshore Wind Accelerator Project. This webinar has been recorded, and you can find it on the Offshore Wind Accelerator page on the Clean Energy States Alliance webpage. And of course, feel free to email me, Val Story, with any questions. Thanks to everyone. Thanks for listening, and have a great afternoon.